Hello students, welcome back. We completed section 2. Now let's go to section 3, linear models. Linear model revolves around the average rate of change because a linear function has the same slope everywhere. So the average rate of change stays constant. If it is a modeling coming from some experimental data or survey or whatever, in that case, not everything will be perfectly same, so there will be some things off here and there, but we want to have more or less the same. So that's what you're looking for, the average rate of change or the slope. Let's see, do we have an example problem here? Okay, let's study this. If you remember the same problem from section 2, that's great, you can skip, but I'll assume you're seeing this for the first time. Alright, stop the playback and read through. Okay, here's part A. A strain of E. coli known as Bohr 397 Rec A441 is placed into a petri dish at 30 degrees Celsius and allowed to grow. The data shown in table 2 are collected, and here is table 2. The population is measured in grams in the time of hours. Plot the ordered pairs x, y in this Cartesian plane and use the average rate of change to determine whether the function is linear. Let's see, we have hours 0 to 5 and the population in grams, and then these are the points, and we can point all those on Cartesian plane. We're gonna get this. Does it look like a line, a linear model? Well, it's a little bit hard to tell. At first glance, it doesn't look like it, but we'll see. If you use technology to get the line of best fit, in other words, it's a line that minimizes the error. The error is vertical difference, not geometrical difference of those points and the line, but vertical difference. Given x coordinate, what predicted y coordinate is here, actually observed y coordinate is over there, so that's the vertical difference. So there is some error here and there, but mostly looks okay. So here it didn't really look like linear, a little bit curved, but if you look at this way, it looks good. Let's see, what if we do some computation? The average rate of change. Basically, this is what you're looking for. F of b minus f of a over b minus a. That's the average rate of change in an interval a to b. So from 0 to 1, you want to do this computation. Okay, let me copy and paste. No. Let's just do it over. So from 0 to 1, 0.012 minus 0.09 divided by 1 minus 0. And that's the quantity you're looking for. So from first hour, 0 to 1. And then how about the next 1 to 2? A and B value will change accordingly. So this will be 2 minus 1. And then instead I'm going to get 0.16 minus 0.12. That's going to be the average rate of change from first hour to second hour. Let me do one more time. And then this time is gonna be third hour to second hour, and then there's gonna be 2 and then 1/6. And then you can do more. 3 to 4, 4 to 5, you can do all those. That's not all. For example, if you want to do 0 to 3, in that case, we can do something like this. 3, 2, 0, and when 0.09. You don't always have to have 1 hour time frame. You can go from 0 to 3 directly, or maybe 1 to 5, for example. So 1 to 5, so denominator becomes 5 minus 1, and then this whole thing is 0.12 and 0.39. Yeah, you have various quantities here. If this had been a linear model, or if this data can be expressed by a linear function, then all these average rate of change, all those will be about the same. Maybe not precisely the same because they're all coming from observation, but more or less the same. What do we actually have? Do we have something wildly different? Then it can't be good. We may be wrong. Even worse, if it is systematically different, then that tells me even more. We are missing something. In this case, not only these do not stay the same, more or less the same, not even they are wildly wrong, they are systematically wrong. In first interval 0.03, in the second interval 0.04, and 0.06, 0.07, the slopes are increasing. So we are missing something, definitely. And then if we put together the line segments, this line segment, and as you go on, we have steeper, steeper, steeper. This is not a linear model. This cannot be explained by a linear function. In fact, this turns out to be an exponential model, and we can use exponential fit like this, and that's something we're going to do in chapter 6 way later, according to this notebook series, lesson 13 and lesson 14, I think. Okay, we went through one modeling problem, and the answer was no. And what were we looking for? We looked for average rates of changes, and then were they pretty much constant, or were they not constant, very different, just wildly different, or systematically different? We went through those kind of things. Now here's a second problem. Stop the playback and read through. The data table in table 3, this data in table 3 represent the maximum number of heartbeats that the maximum number of heartbeats that a healthy individual of different ages should have during a 15-second interval of time while exercising. Plot the ordered pairs x, y in the Cartesian plane and use the average rate of change to determine whether the function is linear. Well, we have this data table, and then we have ages, and then maximum heartbeats, and then we have the points. Well, let's save time. Here are the points. What do you have here? Does it look like linear? Even at first glance, it looks very much like linear. Looks like they're all very well aligned. As a matter of fact, this doesn't really look like a real linear model. Most of the time, you'll have a little bit going up and down here and there, and then maybe some outlier somewhere terribly wrong. Anyway, it looks linear, and use technologies to get line of best fit, and it just goes through all. So this looks very much like a classroom example, not a real example. In real life example, there gotta be some errors, more than that. Anyway, let's do the average rate of change computation. The difference of function value over the difference of age value, the independent value. So first interval, f of 30 minus f of 20 over 30 minus 20. So 47.5 minus 50 divided by 30 minus 20. And if you calculate, we get negative 0.25. And all those give you identical value, which never happens in real life situation. I'm pretty sure this is a classroom example based upon something real, partly upon something real. Somebody must have made it up. In any case, yeah, they're all pretty much the same. In fact, in this particular case, they are the same, so it's a linear model. Okay, here's another model. Stop the playback and read through. The quantity supplied of a good is the amount of a product that a company is willing to make available for sale at a given price. The quantity demand of a good is the amount of product that consumers are willing to purchase at a given price P. Suppose that the quantity supplied and the quantity demanded of smartphones each month are given by the following functions. Well, I don't know about smartphones, but whatever the product. S of P is measured 15P minus 900. So this has positive slope. So if price goes up, then the supplier is more enthusiastic to sell. They want to sell more to make more profit. Now look at demand. Demand has negative slope. So if the price goes up, the more the price goes up, the less the people want to purchase. So the S line will go up, D line will go down, and we are looking for a crossing point. And that's what people say equilibrium. And ideally, that's where the sales are made. Equilibrium price is when they cross each other, and then determines price for which supply is greater. So okay, the S of P is greater above. Well, all these can be answered if you graph those. All right, let's use technology to graph those. Supply is red. No, supply is blue. So as price goes up, the sellers are more willing to sell for bigger profit. Red is demand. As price goes up, people want to buy less. The less the consumers want to buy. And around here, about 200, looks like we have an equilibrium. And that's likely to be the price that sale will be made. So set up S of P is equal to D of P. So S of P is, well, let's see. Supply is blue, so this is blue. S of P is like this. And then D of P is like this. And set them equal to each other, approximately, of course. And then solve it. Well, here's a linear equation. So flip P to the other side, take the like terms together, and divide away. As expected, we get 200. So at 200, we have an equilibrium. That's going to be the fair price. Now, we must find the interval in which, let's see, supplies are bigger. More supply than demand. So blue is bigger. So more supply than demand. Price will go down to the equilibrium. So 200 or greater. So 200 or more. That's the right hand side. Here's a visualization. That part. The right hand side. Okay. So much. So good. Let's see. We have some more example problems. Looks like we'll have to come back and do those in a separate video.